All right, Worthington. Today's little video is going to be on working with systems of equations. And if you can remember a system and inequalities, a system means when you have multiple variables involved in multiple situations. Like I could say I've got markers and I've got erasers and I've got a total of 70 of those in my room, and we can make an equation. But you would not be able to pin down how many markers and erasers I had exactly unless I gave you a second equation and said something like I've got 2.5 times as many markers as erasers. Then you could, I guess, figure out that I had 50 markers and 20 erasers. I think that would be correct. But a system means more than one letter in more than one equation, and you're trying to find the solution for the variables that work in each equation in the system. So there were a couple techniques we talked about. One is using substitution for a variable, which you can do that in a system as long as you have a variable by itself and you know what it equals. Just like a coach makes a substitute for a player, he's got to know what kind of player he has, look down the bench, and say, well, I can pull him off because he kind of equals who I'm taking out, and put him in for him. So here in this first equation system here, I happen to have a couple linear equations, and I've got y equals. So I could very simply take what y equals and put it in for y in the other equation. 2/3 x minus 2 equals negative x plus 6. And the idea is you then get it down to one letter in one equation. So I can do a little work on this. And I'll simplify a little bit here for you. 5/3 x equals 8. Multiply by the reciprocal. 3/5. The answer isn't so much as important as knowing how to do the technique for right now. So you'd have 24/5, and you get an answer, and then you'd be able to plop that in for x, and then you can figure out what y is. I also want to remind you that if you have standard form linear equations, it's a lot easier to just use the technique called linear combinations. I call it elimination, where you pick a letter and you eliminate it from the system by creating opposites in front of the same letter. If you have opposite coefficients in front of the same letter, in math with opposites, they don't attract. They actually kill one another off, and they zero one another out. So for instance, looking at my system here, I like it how they're lined up in standard form. If I could make this negative 4y right here and add it with this equation, the y's would drop out. So you could, what you do here is you do a manipulation of the equation up top, you multiply the whole thing by 2. Now you can do that as long as you do it to everything. You'll create an equivalent equation, so 8x negative 4y equals 16. Then you can combine the equations together and you see the y are just going to drop right out. The idea is always to get it down to one letter in one equation. So I would be dividing by 11, I would get x equals, what's that going to be, 2 and 4/11, I believe. I would need to put that in for x into one of these equations and figure out what y is. Okay? The other way you can do this is graphically. You could take and graph these equations, get y by itself, put them in your graphing calculator, and look where the lines intersect. Okay? But I wouldn't do that if I could use substitution or elimination. Here you can use substitution or elimination. Tell you what, if I was going to use substitution, I would want to make this to be positive y. I would use elimination. I would multiply the top one by 2, and I'd eliminate my y's. Okay? Now, the actual piece of today's lesson that I want to add on is this idea of systems of linear inequalities. So what happens when you have a two-variable equation is you get a line of solution points if there's no power involved. That can lead to an inequality. Okay? So here I'm saying y is greater than or equal to negative 3x minus 1. It's in slope-intercept form. So my boundary is going to be a set of points that forms a line. Okay, when you have a flat plane, the boundary will be a line. If you can imagine a line, I remember me and my sister were young, riding in the back seat of our car. There was kind of this imaginary line. If I crossed it, I'd get whooped. And if she crossed it, I'd try to whoop her. So we kind of stayed on our own side of the car on those long trips. But anyways, -1 is the y-intercept, the slope is down 3 over 1, and I get a set of points that solve the equality. Okay, so, and that's part of the solution set. Y can equal, oops, let's try that again. That wasn't a whole lot better. Y can equal or be greater than 3x minus 1. Now what happens is we are going to be shading on one side of this boundary line or the other. It's called a half plane. Now being it's y and y measures up and down, I'm pretty confident that the shading will go off this way. Okay, but I'm not going to totally fill that in. Now, the second linear inequality is y is less than x plus 2. So the y-intercept's at 2, the slope is rise 1, run 1. This boundary line is going to have to be dotted. I am not including those points as solutions because y cannot equal x plus 2. It must be less than. So less than, if it's y, would be below. So it looks to me, this is kind of a directional thing, north, south, east, west. It looks to me, here are our answers. Okay? So what you got to understand is this, just like if you look at your watch, if somebody says, meet me after 5 o'clock, you have to be able to find 5 o'clock on your watch. And then look, where is past 5 o'clock? Well, it's beyond that boundary. So the boundaries always set the field of play. It's no different than a soccer field. And where we have the boundary lines and then everybody can play in here. Okay, so this is a system of linear inequalities. So what happens is we're looking where the half planes intersect and we find those answers. Okay? So on a state exam, be able to, you won't have to create, but probably analyze a system of linear inequalities. So here would be 1, y is less than 3. So we would have a horizontal boundary line at 3, broken, because y cannot equal 3, less than. I kind of use little arrows to kind of indicate in my mind where the shade's going to go. X is greater than or equal to 1, side to side, x 1. Greater than or equal to. So now I hope you see that really we're down in the southeast right now. We're headed towards Mississippi, Alabama, Florida. Okay, and then I got one more inequality in this system. Y is greater than 2/3 x minus 1. Rise 2, run 3. Dotted boundary because it's greater than. Greater than with y would mean above. And what happens here, you can see it, is you get this little triangle. Okay? So, a system of inequalities is going to produce a zone of answers. It's actually called a feasible region of answers, or a feasible set. There you go. Now, how do you have boundaries? How is this going to look, in a situation for that test? Well, anytime there's a limit on something, you'll have a boundary. Okay? So that's kind of what we're going to have. Now, you could see something like this. If they gave you the graph, can you interpret it and say, well, okay, this is what I'm seeing going on? More than likely, this is the kind of thing you'd see. Which system of linear inequalities is shown by this graph? Well, let's look at it. Looks to me like we got a horizontal boundary, which is a y boundary. So I could say, well, okay, y is at 2 and it's solid, or it's under that. So I'm thinking y is less than or equal to 2. I also see a vertical boundary, which is placing a boundary on x. X looks like less than 3. Those two should be the easy ones. Now the third one is to look at this diagonal and say, well, what's the inequality for that? Well, slope-intercept. Okay? Looks to me like it has a y-intercept at the origin. If you look carefully at the slope, it's going down. If I go from this corner point to this corner point, down 2 over 3. So y equals mx plus b. Y negative 2/3 x. Now, it can equal it, or it is above it, which would be greater than. All right, so this is simply describing where the answers are based off the boundaries and where the shade is off the boundaries. So that is kind of a typical deal right there. Now, I want to show you besides just graphing, I want to show you a problem. So, for instance, I could give you a situation where I would say, we have a problem where we're going to go on a field trip, and the bus holds, I remember this problem from an algebra problem, the bus holds a maximum of 44 adults and students. Okay? We must have at least 3 adults. Okay? Somebody could say, well, could you graph out a set of points that would represent combinations of adults and students that would work for this scenario? And this is a kind of problem that's called a linear programming problem. It's a very basic one, but essentially what I would want to be able to do is say I've got students and I've got adults on this bus, but there's limiting factors. All right? There's a boundary. And one of the things that bounds us is there's only room for 44. So I would be saying adults plus students has to be less than or equal to 44. Okay, now that's not a system, that's one inequality. Secondarily, it says you must have 3 adults. So the adults have to be greater than or equal to 3. So I have a system of inequalities based on information. There's only so much bus space, and I've got to have so many adults. You can graph each one of those. This is in standard form. So if this is 50, we'd be at 44. Every point on that line would be a combination of adults and students that fills up that bus. I cannot be above that line because that would be not enough room for that. I could be below that line, so this would put me kind of in here. But I can't say it's anything because, you know what? I got to have at least 3 adults. So there's a minimum requirement for adults. So when I find 3, that would be a solid boundary line also, and I have to stay at it or above it. Okay? So this zone of answers in here would represent combinations of adults and students that would fit on the bus, and you still have enough adult chaperones so those kids just don't go absolutely crazy. Interestingly, somebody could say, what about that point? And that point there on the outside edge of that feasible region is called a vertex point, and those are very important points because they will maximize or minimize the situation. Okay? This is going to be, if my math is right, 3 adults and 41 students. 41, 3. Now that's an ideal point because it fills up the bus and it gives me my 3 adults. This point right here would really be a minimizing point. Yes, I've got 3 adults, but having 3 adults on a bus seems like pretty much a waste of bus space. Okay? Well, so there's different points in this feasible region. Okay? So anyways, that's a quick shot at systems of linear inequalities. Graph the boundaries to get the shape. How do you get this? Well, you have to read it and translate translate the English into the inequalities. All right, that would be it on systems of linear inequalities.